All right, so welcome to 341 probability. This is lecture 22. All right, so what I want to do today is I want to start talking about some of the inequalities in probability. So these are going to be ways to bound the probability of different types of events happening. And so the big ones for today are Markov's inequality and Chebyshev's inequality. And we're going to talk a little bit about some results you may have seen in calculus, divide and, or maybe even computer science, the idea of divide and conquer and Newton's method. So Newton's method is one of my favorite topics. If you've had 150 with me, you will remember it from that. It's the lecture or the set of problems that moved me from being a physicist to being a mathematician, when you see just how powerful it is. And the reason I want to do this in probability is not just because this is good stuff that you should see, but because it really illustrates the point I'm trying to drive home today. The more you assume about your probability distribution, the more you should be able to say about it. It's not always true, but if you have additional assumptions, if you have additional knowns, it is reasonable to believe that you can deduce more. And so what's the least amount of information I can give you about a probability distribution? Minimum ante for the conversation. Yes. Yeah, there exists a probability distribution. That is the least I can give you. Are there probability distribution? What piece of information would you love to have if possible? The mean. Do there exist probability distributions without a mean? Yes, what's one? Cauchy distribution. So I can't give you the mean because not every distribution has a mean. Okay, so let's assume that we have a mean. Then the next thing you can ask is, what is the consequences of having a mean? And that's Markov's inequality. If you could have additional information beyond the mean, what would you like? Standard deviation or the variance, but that doesn't always exist. And that's going to be Chebyshev's inequality. So the more you know, and then if you know something about the higher moments, that's where the central limit theorem comes into play. That with just a little bit more information, certain sums will converge and be normally distributed. And the question is, why do you have this great degree of universality? We'll be seeing that in a little bit. And so again, the main theme to be thinking about as we go through all of this is that as a rule of thumb, the more we assume, the more we should be able to do. Okay, so let's start off with Markov's inequality. So X is going to be a non-negative random variable with finite mean. So this means that the probability that X takes on a value less than 0 is 0. Then the probability that X is at least A for any positive A is at most the expected value of X divided by A. So sometimes, we write mu sub X for the mean. So equivalently, if this is the probability that we take on a value at least as large as A, so the probability that we're at least as large as A is bounded by the expected value of X over A, then that means that the probability that we're less than A is at least 1 minus the expected value of X over A. So whenever you see a theorem or a statement, you always want to ask, do we really need these assumptions, or do these assumptions just help make things more convenient? Some of the assumptions should clearly be we need. What's one of the assumptions that we clearly need for Markov's inequality? Yes. Yeah, you need it to be a finite mean, or this is just completely worthless, right? If the expected value of X is infinite, well, then the first one tells you it's at most positive infinity. Great. And the second one tells you it's at least negative infinity. Also great. All right. So clearly we need the expected value of X to be finite. What about non-negative? So what you could try to do is to start to try to imagine what would happen if you had a probability distribution that allowed negative values. What might be the most simple one to take with a finite mean? Yeah, so give me a good probability distribution to play with. No, come on, be nice to me. Uniform. What uniform? No, come on, be nice. No. What do you want the mean to be? 0. So let's take something where the mean is 0. Okay. And then what kind of mass do you want to have? It's got to be something symmetric. What's the simplest case you can give me? So, okay, this is something easier than that. Something easier than that. Now, your stuff is equivalent, really, by rescaling. So there's got to be something I'm looking for. All of your distributions are what kind of distributions? Uniform. They're uniform, but there's another word for what you have. You're setting me up, so I'm going to have to do some integration potentially and stuff like that. These are what kind of distributions? Continuous. What might be a better distribution to give me? Well, let's give myself a little bit of freedom. Let's do negative C and C. Whenever you can give yourself a free parameter, give yourself a free parameter. Now we know the expected value of X is just going to be 0. And now if we try to look at this, the probability that you're greater than or equal to any value of A is going to be less than or equal to 0, right? So, the probability that X is greater than or equal to A is less than or equal to 0. It might not even be 0, that's how bad it is. So we need positive, or we need non-negative. Well, if we have a negative A, it's just useless, right? So, again, there's a difference between being wrong and being useless. If I tell you the bound probability is at most 250%, it's a correct result, but it's a useless one. But if I give you, something like this, I could actually get an incorrect result. Because in this case, 50% of my probability is C and 50% is negative C. Okay. So the other thing is, whenever you have something like this, you always want to do sanity checks. So the first thing is always check units. So what units do you want X to be in? If we're doing a problem like this, what units should we take for X? Got to give me anything. Inches, okay. I would probably do meters, but we can do inches. If X is in inches, then what's the expected value of X? Inches. And what would A have to be? Inches. And so the expected value of X divided by A is unitless. Good, which is good. Because it's supposed to be a probability. Probability is supposed to be a number. So the unit analysis works. The next thing is to think about what choices of A will this be useful. If I take A to be less than the expected value of X, then my upper bound is greater than 1. It's not wrong. It's just useless. Williams is going to kick whose ass next, or this upcoming Saturday? Amherst, right? And if I tell you, Amherst will score less than 250 points, that is at least technically providing some information. There was a football team that scored 222 points once. So it's almost surely, though, useful. If I tell you Amherst will score no fewer than -5 points, that's clearly useless. If I tell you they'll score no fewer than 0 points, that's still useless. Now, if I make that an upper bound, then of course now it's useful. So you always want to think about what values can you get something of this out. If A is less than the expected value of X, this is useless. It only starts kicking in once A is greater than the expected value. Well, that makes sense. Can you give me an interesting distribution where the probability that X is greater than or equal to A is exactly equal to the expected value of X over A for a key value of A? So if A is less than the expected value of X, this is useless because it's a bound of over 100%. What if A actually equals the expected value of X? Then this would give you the probabilities at most 1. Is it possible for the probability to be 1? Could you give me a probability distribution where all of its mass is at the expected value? Sure. That would work. So what that shows you is that this is in some sense sharp. We can't get something better in general. And then we can start trying to look at some extreme cases. So a good extreme case to look at is, let's imagine here's 0, and here is the expected value of x divided by 1 minus p. And let's say p% of the time we're here, and 1 minus p% of the time we're here. What would be the expected value of this random variable? So p% of the time you're 0, 1 minus p% of the time you take on the expected value of x over 1 minus p. So what will the expected value be? It's just p times 0 plus 1 minus p times the expected value of x of 1 minus p. So this has expected value of x. So this is a random variable whose expected value is the expected value of x. And so again, it's much better to do some simple discrete distributions like this rather than a continuous distribution to just get a feel of what's going on. If I do it like this, as I get p closer and closer to 1, I can make as much of my probability as I want at 0 by putting a small amount of probability very far down. Right? You imagine, a Bezos or a Gates walks into this room and really just messes up the, lifetime savings distribution, right? So if I have just a few extreme values, that can greatly change the mean. And so in a situation like this, I can have as much of my probability as I want, as close to 0 as I want. And so just in terms of trying to get a sense of, well, what I want the probability of x to be greater than or equal to a. Well, if a is greater than the expected value of x, this starts to give us some reasonable results. But over here, I can have this as close to 100% as I want. So if you just go through the book, does this in detail, you can see that by looking at extreme cases like this, we really can't do much better because I can come up with some strange examples. And I really want you to get into the habit of trying to do this. Look for extreme cases, put things as far away as you can to just try to get a sense of what's going on. All right, so let's try to prove this. So the proof of Markov's inequality is not too bad. And it uses the key fact, if x is greater than or equal to a, then x over a is greater than or equal to 1. And now we can begin to see why we might want a to be positive, or a random variable to be positive or non-negative, because if we have a negative sign, we can flip inequalities. So if I want to calculate the probability that x is greater than or equal to a, this is just the integral x goes from a to infinity of the density of x dx. Okay. Now, what is the expected value of x? This is just the integral from 0 to infinity of x times the density of x dx, as it's non-negative. Now, if I integrate from 0 to infinity, I get the expected value. What would happen if I only integrated from a to infinity? Almost not, you can't say less than equal to. So this would be greater than or equal to the integral x goes from from a to infinity of x fx of x dx. Because we're throwing away potentially some of the probability. We may not have thrown away any of the probability if there's no probability less than the mean. But we know I can write this as this is just equal to the integral x goes from a to infinity of a times x over a fx of a dx. I've just multiplied by 1. And just, having fun, using the multicolors. Yes?
Fx
Oh, that should be an X, yes. And now we know that X over A is greater than or equal to 1. And so this is now going to be greater than or equal to A times the integral X goes from A to infinity of Fx of X dx, which is just A times the probability that X is greater than or equal to A. I'm sorry, greater than or equal to A. And so now we get the probability that X is greater than or equal to A is less than or equal to the expected value of X divided by A when I just divide. And that's the proof of Markov. So what we do, it's really straightforward, is we just throw away probability. And then you always want to ask, where did we use the fact that we have a non-negative distribution? Well, we want to be able to just replace the X over A with 1. What if X over A were negative? If we throw that away, what do we do to the problem? What do we do to the integral if we throw away something that's negative? So if you throw away something that's negative, what do you? We're not dividing. So let's say we actually went all the way down to negative infinity. And now we have the region where X over A is a negative number. And so we throw away the integral corresponding to X over A being negative. So if we're throwing away the integral of a negative quantity, when we throw that away, what happens to what you have left over? Does it go up or go down? It goes up. You know, if I throw away all of your debts, you now have more net worth. So that's where we're using the fact that we have a non-negative distribution, so that when we just throw this stuff away, it's not going to make things larger. So you always want to ask, where are we using it? Because we know from the previous page that we have to use somewhere that it's non-negative. So we use non-negative when we throw away integral, integral over some region. Okay. And so we have now proved Markov's inequality. And then the next thing to do is to just do some problems. I'm not going to do this problem. This is in the book. This is just here so that the slides are self-contained. One of the things you can do, and again, you know, there's just too much material to cover in a lecture, is you could start asking questions. Well, what's the probability maybe that we're L times the expected value? And you can play games like this, and you can get that the probability that you're L times the expected value is at most 1 over L. So this is decaying. So the probability that you're at most 10 times the mean is at most 1/10. The probability that you're most 100 times the mean is 1 over 100, which makes sense. You know, if you're really, really far from the mean, that's going to push the mean up a lot. So you can't have too high of a probability of being too far away, or your mean is not what you thought it was. On the other extreme, we can't have negative values. So the worst you can have is 0. So when you're trying to figure out what's the contribution, you don't have to worry about something being very far to the negative and balancing something very far to the positive. And that's where, you know, we are crucially using that we have something that's non-negative. Okay, so the next is Chebyshev's inequality. One of my goals in life, which will never be met, is to work on how Chebyshev's name is spelled. There's at least 40 plus acceptable spellings of how you translate his name from Russian into the English alphabet. He has a tremendous number of theorems, and I would love to use a different spelling for each theorem, so that when you say by Chebyshev's inequality or Chebyshev's theorem, it's clear what you mean. You know, this is one of the mathematicians where there's lots of different things attached to it. So what we're saying here is X is now a random variable with finite mean and finite variance. Then for any k greater than 0, the probability that we differ from the mean by at least k times the standard deviation is at most 1 over k squared. Or equivalently, the probability that we're within k standard deviations is at least 1 minus 1 over k squared. This is a truly wonderful result. Now, your first thought should be to compare this to Markov. You know, does this do better? If you had to guess, what would you think? you think it does better, worse, or about the same? Hopefully it does better. Why do you think it might do better? You have more information, right? If you have more information, you should hopefully be able to do better. Is it possible to do worse? It is, but then that means you're arguing in a horrible, horrible way, right? Although there is a difference. What's the difference? It's not just that X has a finite variance. What else are we assuming about X now? It doesn't have to be positive. Oh, so there's a little bit of a difference between this and Markov. And so maybe, yes, we have some additional information that we have a finite variance, but we no longer have the fact that it's non-negative. And so maybe that trade-off could result in Markov winning. Okay. So the first thing is always is, the sanity checks. What about the units? What unit should we use for X? Meters, okay. So we'll use meters this time. It makes sense to compare how far away am I from the mean in terms of standard deviation. The standard deviation is the natural scale to study how far we're moving. So this is a really natural thing to look at. How far am I away from the mean? Well, I don't want to measure this in an absolute scale. I want to measure it relative to the standard deviation because that tells me the correct scale of the fluctuations. So looking at k times the standard deviation is a really good choice of something to study. And as you go further in math and stats, you have more and more choices of what statistic to look at, what things to study. This is an excellent choice. Okay. And then we can also ask these questions about values of k. If k is less than 1, what do you get for your bound? So what would be your bound if k is less than 1? I'm sorry, it would be greater than 1. Is that reasonable? Is that a reasonable bound that the probability is? Yes, it's reasonable. It's at most 150% sure. Is it useful? Hell no, right? You would never use this with k less than 1. Even at k equals 1, you're getting a bound of at most 100%. There's usually faster ways of getting a bound of 100% than going through advanced arguments, right? So it's correct, it's just not useful. As k starts to get larger, now all of a sudden, we're in the situation where this could be valuable. Okay. So now we can try again playing games like extreme cases. We could assume we have a distribution that's, say, half the probabilities at minus c, half the probabilities at plus c. You can play those games again. And you can try to build up some intuition. With a little bit of work, you can show that the probability that you're at least L standard deviations from the mean is decaying like a constant over L squared. And for Markov, you'd be getting something decaying like 1 over L. So it is decaying better than Markov. So this is valuable. Okay. So let's prove this. There are 2 ways to prove it. They're essentially identical. And so it's all a question of how lazy are you. I'm going to prove it by using Markov. And that's probably why I'm doing them Markov first and then Chebyshev, because I can show how Chebyshev follows immediately from Markov. Well, if I want to use Markov, I need to have a non-negative random variable with finite mean. I can't use X. I have to use something related to X. So can anybody give me something related to X that's non-negative? Absolute value of X. So I could try y equals the absolute value of X. But I want to measure things about the mean. So maybe I'll try X minus the expected value of X. So that's a good thing to try because this is non-negative. Unfortunately, it's not a great quantity to look at in terms of just being able to do calculations because we have an absolute value. What else are we assuming in this problem? We're assuming we have a finite mean and we're assuming we have a what? Finite variance. How do you calculate the variance of x? So it's what? Okay.
Expected value of x squared minus expected value of x all squared.
Okay. So one definition is it's the expected value of x squared minus the square of the expected value of x. And what's the other way of writing it? Integral.
X squared plus x of x dx.
Well, no, that's just converting it to integral form. There's another definition of variance. One is the difference of two expected values. What's the other definition of variance?
Sum of all the points around it.
Yeah, or we're doing integration, so it would be the integral. So it'd be x minus the expected value of x squared times the density. We're trying to figure out a good choice for a non-negative random variable associated to x. The first thing that came to mind was to look at the expected value, I'm sorry, x minus the expected value and take the absolute value of that. That's going to be non-negative. But we have information about the variance. And the variance involves integrating x minus the expected value of x squared. What can you tell me about x minus the expected value of x squared? It's non-negative. What does this suggest we should take for our value for our new random variable? Yeah, so let's try, W for Williams is equal to x minus, or when, which is coming soon, x minus expected value of x squared. This is a non-negative random variable. What is the expected value of W? It's just the variance, right? It's just the variance of x. Because if you look at how we define W, if we now calculate the expected value of W, it would just be x minus expected value of x squared times the probability. It's just going to be the variance. So by Markov, we now get the probability that W is greater than or equal to what? Greater than or equal to A is less than or equal to the expected value of W over A. So this is the probability of, I'll write it as x minus mu of x squared greater than or equal to A is less than or equal to the variance of x squared over A. Is everybody comfortable with this? We're just substituting into Markov. Well, I have x minus mu of x squared is greater than or equal to A. I can just take the square root of A. So take square root, and when we do that, that goes away, and we get this to the 1/2. So what should we take A in terms of K and sigma and all that stuff? So we want A to the 1/2 to equal K sigma X, right? So sigma X squared over A is just 1 over K squared. Because we want this here, we want the square root of A to equal K sigma X. And that's exactly in the form that we need. So if we take a to the 1/2 to be k sigma, then if we square both sides, we get sigma x squared over a is just 1 over k squared, and that finishes the proof. And now we just substitute in. And there's the proof. So Chebyshev follows immediately from Markov. The difficulty was finding how to use Markov. Markov requires us to have something that's non-negative. So if we want something that's non-negative, we need to find a good way to view it. Any questions about this? So I really want to emphasize the thought process today as to how do we come to look at stuff like this? You can always look up in the book statements of theorems, but I really want to go through why are these natural things to try. And then at the end of the day, when we have our stuff, we just have to then convert to the form of Chebyshev. That we want to measure things in terms of how many standard deviations away are we? So it's going to just be k times sigma, x has to be a. All right, any questions about this? All right, so this is Chebyshev, this is Markov. Okay. You can also prove Chebyshev directly. If you look at this, it is essentially the same proof as Markov. And so I want to calculate what's the probability we're at least k standard deviations away. So I integrate over all values such that x minus the mean in absolute value is at least k standard deviations away. And I'm just integrating the function 1 times the density. Well, because x minus the mean in absolute value is at least k sigma, that means x minus mu of x over k sigma x squared is at least 1. So this then becomes an upper bound. It's again very similar to the Markov. Well, now I pull out the k squared sigma squared, and I have the x minus mu of x squared. Oh, well, x minus mu of x squared, this is looking a lot like the variance if I just integrate it over everything. I'm only integrating over a subset. Let me extend the integration. That can only make things larger because I have something that's non-negative. And now I just get the variance sigma x squared, which cancels with the sigma x squared outside, and there's the 1 over k. All right, so that finishes the proof. So, again, I'm doing the integration slightly differently than I did in the Markov case. You can write a lot of these integrals many different ways. The goal is to try to just find a way that just clicks with you. All right. Any questions on what we've done so far? So if I have a standard normal, if I want to calculate what is the probability I'm at least 10 standard deviations away, I get the really small value of 1 over 100. But that's still 1%. Does anybody know the actual probability of being that far away? It is extremely small. Oh, it is showing up over here. Okay. N integrate. We'll do 2, 1 divided by square root of 2 pi exponential negative x squared over 2. X goes from 10 to infinity. So, the correct probability is on the order of 1.5 times 10 to the negative 23. Chebyshev gives us 1%. All right, not even close. Okay. So the whole point of this is, just because we have some bounds doesn't mean these bounds are anywhere near reality. So why does Chebyshev fail so miserably when we try to do it, with the central, with the Gaussian? The reason is Chebyshev is working with any probability distribution with finite mean and finite variance. Because it is so accepting of distributions, it has to work in all these extreme cases as well. The central limit theorem is going to do a much better job in terms of estimating probabilities because it's restricting to a Gaussian, and then you can use properties of the Gaussian. So the Chebyshev result, while it's sometimes bad, the reason it's bad is because it is so applicable. And because it's so applicable, it's not going to be as good as a result that's tailored to what you're trying to do. So that's one of the big themes to get from today. All right. So what I want to do now is talk a little bit about divide and conquer and Newton's method. These are slides from a talk I've given over the years. I first gave it at Williams and Mystic. Most recently, I think I gave it at the Michigan Math Club, although I've actually given analogs of this to both my kids. All right. So much of math is about finding roots. So if I give you a linear equation, ax plus b equals 0, this is not that hard for you to solve, x equals negative b over a. If I give you a quadratic, we have completing the square, which we've used a few times, and you get negative b plus minus square root of b squared minus 4ac over 2a. There are explicit formulas for the cubic and quartic. They get messy. There is no general formula for the quintic and higher. That's a great result in Galois theory and abstract algebra. So instead of trying to solve the problem exactly, we lower our goals and try to just approximate. Just for fun, here are the 3 roots of a general cubic. Please have this memorized by the time you die. There will be, I guess, no real consequences if you don't. Now, you could make things a little bit nicer without loss of generality. You could rescale things so that a equals 1. You can translate so b equals 0, but it's still going to be a nightmare. And if you think that's bad, here's just one of the roots for the quartic. Okay. It's beautiful that there are such solutions and you have explicit parameter dependence, but we don't have this for degree 5 and higher. So what I want to do now is I want to talk about 2 different ways to find roots. So the first method is divide and conquer. And so imagine I have a continuous function and I know it's negative around 0 and I know it's positive around 1. What must happen in between? It has to hit the real line at some point. You can't discontinuously move. What TV series is famous for being able to discontinuously move from one place to another? Star Trek. And the reason the transporters were invented is they actually didn't have a budget for the premiere to have a shuttlecraft to go down to the planet. So it's like, well, what if we just press a button and then all of a sudden they're on the planet? That would save us having to build the shuttle set. So, okay, we now have the transporter. Anybody know how the transporter works? Well, but what makes the transporter work? So Professor Strzok and I are teaching a class, winter study on the science of Star Trek. They have Heisenberg compensators to compensate for the Heisenberg uncertainty principle. Beautiful name. All right, so we know that there has to be a root somewhere in between. And so what we do for divide and conquer is we basically just keep going halfway and we check. So imagine it's negative at A, positive at B. Look at the halfway point. If it's positive, then you know there's a root somewhere between A and A plus B over 2. If it's negative, there's a root somewhere between A plus B over 2 and B, and you keep going. So can somebody choose a random day, in the year? Somebody have a random day?
May 30th.
Okay. Probably should have said keep it quiet, but okay. So let's see if I can guess May 30th. So I will be a moron. Is it January 1st? January 2nd? January 3rd? I will eventually get it, but it could take me 365, 366 guesses. Or I can use the divide and conquer, also known as binary search. Is it July 1st? Earlier or later? Earlier. So now with one guess, I've eliminated half the time. So January, February, March. February is a little bit short. So I'll go with, is it April 1st? Earlier or later? Later. And again, with that, I now eliminate half of what's left. 2 to the 10 is 1,024. I should easily be able to get it in 10 questions. So you can do this to amuse little kids. I can guess your birthday in at most 10 questions. So binary search isn't that bad. Now 2 to the 10th is 1,024, which is approximately 1,000. So what that means is every 10 iterations of divide and conquer gives you about 3 more decimal digits. How many megabytes are in a gigabyte? It depends who you talk to. I think it's often 1,024. If you look at just the words giga and mega, it should be 1,000. But because computers work base 2, it's a little bit more convenient to have it 1,024. And if you go through and just try to do divide and conquer, let's say we want to try to calculate the square root of 3. We know it's going to be somewhere between 1 and 2. And so we can just keep going, looking at left endpoint, right endpoint. And we can see after 10 iterations, we know that the square root of 3 is somewhere between, I think, 1.730 and 1.7324. The correct answer is 1.73205. So that's not horrible. But if I wanted more digits, and if I wanted 3 more digits, I have to do this 10 more times. Now, for something like the square root of 3, I'm trying to solve the polynomial x squared minus 3 equals 0. So as long as I'm using rational points, I'm going to just have rational numbers, and I just have to check and see is it positive or negative. So the computer can actually do this without too much trouble, but it's not going to be super fast. So let me talk about Newton's method. So the big idea in calculus, at least first semester calculus, is any complicated function locally looks like a straight line. And so what we can do is we can approximate our function with the tangent line. And so this gives us the next guess. So what's really going on, and the picture's on the next page as well, here is my axis, here's my function, here is some point x naught, here's a point, and I calculate, the point over here is x naught, f of x naught, and the slope is f prime of x naught. And then I just see where does that line hit the curve? Where does that line hit the x-axis? And that's my next guess. So just writing it out a little bit better, here is my function. Here's my point x naught. I draw the tangent line at x naught, and I just flow down on the tangent line until I get 0. And so the equation of the tangent line is going to be, y minus f of x naught equals f prime of x naught, x minus x naught. So when y equals 0, call that x1. And so we would get x1 equals f of x naught plus f prime of x naught. Oh, so that's not x1. That's going to be 0. X1 minus x naught, solve for x1. So we can just flow on the tangent line. And the hope is that it's not going to be a terrible approximation. What should we do next? Yeah, lather, rinse, repeat. We do shampoo mathematics, right? Now we go up to x1, flow up, draw the tangent line, see where it hits. What do? Do it again, do it again, do it again, do it again. And you can actually write down, if I start off with the equation f of x is x squared minus 3, after you do a little bit of algebra, you see the next guess is 1/2 xn plus 3 over xn. Well, if you think about it, if you were really lucky, what value for xn would you have? Yeah, if you had the square root of 3, you'd have root 3 plus 3 over root 3. That's just twice root 3 divided by 2 is root 3. So if you happen to be at the root, you stay at the root. And if not, you're basically averaging, where you are and essentially the reciprocal of it. So this is at least a reasonable thing to be trying. The question is, how quickly does it work? And so if we start off with the square root of 3, and if we guess 2, that's not a terrific guess, it's a reasonable guess. The next iteration is 7/4, so 1.75. The next one is 1.73214, which is pretty close. The next one is, it's actually easier for me to read over here, which is sad, is 1.73214, then 1.7320508, 1.732050807. So you can see just how good it is. By the time we get to the 5th one, you have to go all the way down to, I have no idea how far down that is. Essentially, every time you do Newton's method, every iteration, you double the number of decimal points. Absolutely amazing. Yeah, this is why I moved from physics to math. When I saw an algorithm that worked just this well, if you want to approximate the square root of 3, just doing 5 iterations, we now have a rational approximation. Even 3 iterations, you're essentially at the level that most calculators will give you. Amazing, how powerful this is. So there's a lot of stuff you could then do with this. And just, we've got like 4 minutes left. So if I give you the function x squared minus 1, there are 2 roots at 1 and -1. Let's color the one at -1 red, the one at 1 blue. If I choose a random point and I keep applying Newton's method, I can ask, where do you think we converge to? So which ones do you think converge to -1, Which ones do you think converge to 1? Which ones do you think don't converge? We don't have much time. I need fast answers. What do you think goes to -1? Everything that's negative goes to -1. Everything that's positive goes to 1. And 0, well, Newton's method blows up there, so it shouldn't even do anything. So you are correct. Good intuition. We could then try to do a cubic, x cubed minus 1. We can factor it. There's 3 complex roots. When you take x equals 1, it's going to solve x cubed minus 1. So now you have a quadratic. You can do long division if you really want to. So there's 3 roots, and I've plotted them. Which ones do you think converge to the red, which to the green, which to the blue? What do you think the rule is? You go to the red if you are. So give me a nice simple phrase as to how you determine which route you go to. You go to the route that is closest, right? So we can divide the plane into 3 regions and just go to whichever route is closest. Unfortunately, if you actually try to do this, you actually get a fractal picture. And what that means is if you tweak yourself ever so slightly, you can wildly change where you go to. This is an extremely important lesson to be aware of. They first discovered stuff like this in terms of orbits of planets, I believe. Then there was big stuff with trying to model the weather. When you look at some of the models that are now being used for climate predictions, this is something you have to be extremely careful about. So I'm not saying anything one way or another about the science. I'm just saying you have to be careful to how sensitive is your model to values of parameters. No, the dark spots are just the computer says, screw it. So on the real axis, it's not too bad to see what's going on. Let's see if I can get this to quickly open. Actually, I think a better way to do this is over here. Is this still showing on the screen? Okay. We still have half. All right, so we'll skip the ad. I can't remember if this has cheesy music or not. I often have the volume on mute. Okay, this one doesn't have cheesy music. And so this is showing you what's happening as you zoom in. Can you see it even though the lights are on? Yeah. Okay, so as you're zooming in, you can see one of the great features of fractals is just this incredible self-similarity, that you see the same behavior on very different scales. But the key thing is a slight change in some of the initial values leads to wildly different behavior. And then there's a lot of terrific mathematics going on here. I want you to be aware of this as you're going to apply probability and try to model things, but just how careful you have to be. All right, so this is a good place to end.